Hi, my name is Aurélien Manchon. I'm an Associate Professor of Material Science and Engineering at KAUST, and this is the first lecture of my series of courses, entitled Introduction to Spintronics. In this lecture, we are going to slowly dive into the origin of magnetism in matter. Since magnetism comes mostly from the electronic contribution, we are going to focus on the interplay between the spin and the orbital angular momenta, and see how they cooperate to create an overall magnetic moment at the atomic level. In the second part, we are going to review the most important interactions that govern the magnetic configuration in matter. And finally, in the last part, we are going to review a few selected examples taken from the vast zoology of magnetic materials. So if you are ready, let's start. As we have seen in the introductory lecture, a magnetic moment is proportional to an angular momentum. When looking at an electron, we know that the angular momentum has two contributions, the spin and the orbital. The spin can take two values, plus h bar over 2 and minus h bar over 2, and the orbital angular momentum is simply an integer times h bar. Well, when you put the electron in an electrostatic potential, let's say in the radial field of a nucleus, well, this potential will determine the magnitude of the orbital angular momentum, and therefore it will govern the overall magnetism of the electron. So let's have a closer look at it. The orbital angular momentum is a vector defined as the cross product between the position operator and the linear momentum operator. To better understand how the orbital operator works, we can compute the commutator between two different components. If we do that, for instance between the x and the y component, we obtain the z component with a factor I h bar in front. On the other hand, if I take any of the three components and perform the commutator with the square norm of the orbital vector, I get 0. It is convenient to write these algebraic properties in a more compact manner. The first relation here involves the cross product between two non-commuting operators. The second relation has a very important consequence. Because the individual components and the square norm of the orbital momentum operator commute with each other, it is possible to define a quantum state that is dissimultaneously an eigenstate of this component and an eigenstate of the magnitude of the orbital operator. The direction of the component we choose to determine the eigenstate is called the quantization axis. Actually, these rules apply to any angular momentum operator, not just the orbital angular momentum operator. So if I define an angular momentum J, I will find the very same commutation rules. Therefore, the eigenstate of the angular momentum is characterized by two quantum numbers, minuscule j associated with the magnitude of the angular momentum j squared, and mj associated with the projection of the angular momentum along the quantization axis. mj can adopt any discrete values between minus j and plus j. What we have seen until now are the fundamental properties of the angular momentum operator in quantum mechanics. These apply to both the spin and orbital momentum. Now we are going to see how useful are these properties in the context of condensed matter physics. And to do so, we are going to consider the specific case of the hydrogen atom. So why the hydrogen atom? Well, simply because it is the Rosetta Stone of quantum mechanics. What do I mean by saying that? Well, you might know that Rosetta Stone is this amazing piece of carved stone made back in 196 BC and rediscovered in 1799 during Napoleon's expedition in Egypt. This stone records a decree from Egyptian king Ptolemy V. The top part of the stone is written in ancient Egyptian, written in hieroglyphs. The middle part of the stone is written in ancient Egyptian using demotic, and the bottom part is written in ancient Greek. The analysis of the interconnection between the three texts allowed Thomas Young and Jean-François Champollion to decipher the hieroglyphs. Well, the hydrogen atom is pretty much like that. You might remember in the introductory lecture that the analysis of the spectral lines of hydrogen led to the discovery or to the formulation of the old quantum mechanics by Bohr and Sommerfeld, and later to the discovery of the electron spin. What we're going to see now is that the understanding of the orbital contribution to the electron wave function in the framework of the hydrogen atom is at the basis of our understanding of magnetism in matter. Let us consider a hydrogenoid atom, that is to say, an atom that has the same central potential as hydrogen, Z here being the number of protons of the nucleus. In the spherical coordinates, the kinetic term adopts a complex form that involves the polar and azimuthal angles theta and phi. Interestingly, one can recognize that these two angular terms are actually proportional to the square norm of the orbital angular momentum, L squared. We end up with a Hamiltonian that depends on the radius r only and of the orbital momentum operator L squared. Therefore, we can look for a wave function that is composed of a radial part that only depends on r and of an angular part that only depends on theta and phi. So here is our wave function with its radial part and its angular part. Let us focus on the angular part first. As we have seen previously, this part must be an eigenstate of the orbital angular momentum operator and should therefore fulfill the following relations. Here, the quantum number L is called the orbital quantum number, and the quantum number NL is called the magnetic quantum number. We can determine the exact form of the polar and azimuthal dependence by writing explicitly the operators Lz and L square in spherical coordinates, assuming that we can again separate the angular part of the wave function as a product between two functions, one depending only on the polar angle theta and the other one depending only on the azimuthal angle phi. Okay, so let's do that. We then obtain a couple of eigenvalue equations that can be solved using standard mathematical tools. And we obtain the angular part of the wave function explicitly. Here. The azimuthal angle is simply a phase exponential I ml phi. But the polar part has a much more interesting structure and can be written in terms of Legendre polynomials. So in summary, the angular part of the eigenstate depends on two quantum numbers L and ml and has this really nice expression. I say really nice not because it's ugly, and frankly it does look freaky, but because it reflects the complex distribution of the electron around the nucleus. This complex distribution is called a spherical harmonic, and it will be very important to determine the band structure of real matter and its magnetic properties. To be more concrete, let us look at a few selected states. For an orbital quantum number L equals 0, the angular part is a constant, which means that it has a spherical symmetry. For an orbital quantum number L equal 1, the polar dependence appears under the form of cosine theta and sine theta. And finally, for an orbital quantum number of L equal 2, this dependence appears under the form of cosine 2 theta and sine 2 theta, and so on and so forth. In cubic crystals, or when the ions possess an environment with cubic symmetry, it is often convenient to represent these orbitals in Cartesian coordinates. These are the cubic harmonics. The most common orbitals we will encounter in this lecture are the s, p, and d orbitals, which are written as a function of the spherical harmonics. We recognize that the s orbital has this very nice spherical symmetry. Now, you can notice that the p orbitals with an orbital quantum number of 1 are elongated along the x, y, and z directions. Now, the d orbitals with an orbital quantum number of 2 present a much richer structure. The dxy, dyz, and dzx orbitals seem like a reminiscence of the px, py, and pz orbitals we just discussed. And the two remaining orbitals, the dx2 minus y2 and dz2, point respectively in plane and out of plane. These orbitals are responsible for the magnetism of transition metals. Okay, now we have taken care of the angular parts of the wave function. Let us take care of the radial parts. We go back to our Schrödinger equation and solve it for the radial function. Notice now that the operator of orbital angular momentum can be written explicitly in terms of the orbital quantum number L. So in other words, I replace the L square operator by L times L plus 1. And what we see straight away is that the orbital quantum number contributes to a repulsive potential. The higher the orbital quantum number is, the more repulsive the potential. When we compute the radial part, we realize that it now depends on another quantum number L, which is called the principal quantum number, and that must be larger than the orbital quantum number L. For an orbital quantum number of 0, the radial parts adopt the following forms, which are composed of a polynomial times an exponential decay. Of course, we are looking for bound states, meaning that the electron is attached to the nucleus, and away from it, the wave function vanishes. These three solutions are represented in this graph. One can see that the state with the smallest principal quantum number is located close to the nucleus, while the states with larger principal quantum numbers are more and more delocalized. Let us now look at the impact of the orbital quantum number on the radial part. As I said, it contributes to an effective repulsive potential. So if we compute the radial part of the eigenstates for n equals 3 and different orbital quantum numbers, we obtain the following solutions represented on the figure. You can see that the 3s wave function presents two nodes and penetrates closer to the nucleus. In contrast, the 3p wave function has one node and the 3d wave function has none. The 3p and 3d wave functions are shielded and remain localized away from the nucleus. So a higher orbital angular momentum results in more shielding and a more localized wave function. This observation is super important in the context of magnetism, because this localization will result in an enhanced electron-electron interaction that is at the origin of magnetic exchange. Now that we have looked at the complex structure of the orbital angular momentum, we can take a break and look at the much simpler structure of the spin angular momentum. Once again, since the spin is an angular momentum, it fulfills the usual commutation rules, which determine the eigenstate of the spin operator. This eigenstate depends on two numbers, the spin quantum numbers and the secondary spin quantum number, which amounts for the projection of the spin momentum on the quantization axis. If we consider an electron with spin 1/2, we end up with two states, -1/2 and +1/2. These two states will accompany us until the end of this lecture series. If now we consider a spin 3/2, then we end up with four eigenstates, -3/2, -1/2, +1/2, +3/2. When it comes to spin dynamics, it is very convenient to look at the part of the spin wave function that is transverse to the quantization axis. To do so, it is common to define what we call a ladder operator, which is a linear combination of the Sx and Sy components. Of course, such a ladder operator can also be defined for the orbital angular momentum or any angular momentum in general. You can now look at how the various components of the spin operator act on a given eigenstate. You can get these formulas by yourself or in any quantum mechanics book. You see that the z component, which we choose our quantization axis, doesn't do much, by definition, simply because psi is an eigenstate of Sz. However, the latter operator increases or reduces the secondary spin quantum number by 1. That's the reason it is called a ladder operator. So, one can express these spin operators in terms of a matrix, which is called a Pauli matrix. In the case of an electron with spin 1/2, I have the following three Pauli spin matrices: Sz, Sx, and Sy. The coefficients are given by the expressions above. These matrices will be your best friend for the remaining of the lecture. We have looked at the structure of the orbital contribution to the electron wave function in the case of a central potential, and we have seen how to represent the spin using Pauli matrices. Now comes the question, what happens when an electron possesses both orbital and spin momenta? What is the total angular momentum? Well, the answer looks quite simple. It's simply the sum between the orbital and the spin angular momenta. Well, let's have a closer look to it. But what about the composite state? How does it look like? This new composite state is an eigenstate of the total angular momentum J associated with a secondary quantum number Mj. J is the sum of two vectors, J1 and J2, so it can take all the discrete values between the absolute value of J1 minus J2 and J1 plus J2, while Mj adopts all the discrete values between minus J and plus J. If we consider two electrons with spin 1/2, we end up with one state with total angular momentum J equals 0 and three states with total angular momentum J equals 1. The state with angular momentum 0 is called a singlet, while the three states with angular momentum 1 is called a triplet. Since the total angular momentum of a singlet is 0, you can think of it as if the spin of the two electrons were antiparallel. In the triplet case, you can picture it as if the spin of the two electrons were parallel. Now, I can take another case and consider an electron with spin 1/2 and angular momentum L equals 1. Then, we end up with four states with total angular momentum J equals 3/2 and two states with angular momentum J equals 1/2. This situation is typically encountered in semiconductors such as gallium arsenide. The question we haven't answered is how to connect the composite state with the individual eigenstates. In other words, how to calculate the composite wave function from the wave functions of the individual components. Well, this is achieved through what is called Clebsch-Gordan coefficients, which fortunately are tabulated. We have seen how to represent a state with both spin and angular momenta. Now the next question is, what happens in condensed matter when we have crystal field, electron-electron interaction, spin-orbit coupling, Zeeman effect? Well, that's the topic of part B. So let's move on.